inductors, inductance. So this chapter will be kind of analogous to the chapter, what I believe it was chapter 24, which we covered on capacitors and capacitance, and chapter 25, which was on resistors, resistance. So it's nice to kind of compare them and say, okay, what are their differences and what are their similarities? And also this chapter has a little bit of the next chapter, which is RC circuits. RC circuits, that chapter, because now we can have RL circuits. We can have inductors in there. So it's got a little bit of all those other chapters. So if we start out with the capacitance chapter, we can say, how did that chapter even begin? We can see that we said we first began with defining the capacitance of a capacitor, Q over delta V. And then we talked about its units, which is farads. And then we, using the definition of capacitance, we then found the capacitor of parallel plate capacitor, A E0 over D. We found the capacitance of cylindrical capacitors. So this is parallel plate. Cylindrical capacitors look like this. And then it had an outer cylindrical shell. So you had three kind of basic capacitors. And that one was, what was the formula? I don't remember now, but we don't use it that often. But it's something like ln of, I think it's ln of R2 over R1, something like that. And then we have probably, let's see here, ln R1. I think there's something like R1, R2 up there, but I'm not really sure. So it's something like that. So we derive the capacitance of a cylindrical parallel plate, and then spherical, which is a sphere surrounded by a spherical shell. And then that one was, I believe, I think that one was like R1, R2 over R2 minus R1. And then there was something like E0 was up there. It was kind of similar to this. Yeah, that seems reasonable. I just don't remember, the cylindrical was a bit different. So then you have the three kinds of capacitors. Then we mentioned, well, what happens when you put a dielectric in there? Dielectric constant kappa, right? Then we saw that the capacitance goes up by that factor, kappa, kappa, and then kappa. So if you put a dielectric, then the next thing we saw is how do capacitors add up in series and parallel. In series, it was like this. And then in parallel, it was like this. And then we put capacitors in circuits, and we answered a variety of questions based on that. Like battery, we put it in a circuit, C1, C2, and we said, okay, what's the net capacitance of this circuit? What's the charge of each? What's the energy stored in each, right? Or you have a variety of other problems, like you have a charged capacitor, initially charged, that's placed with another uncharged capacitor. And then the problem might say, well, what's the final voltage of each? and what's the final energy of each. So this is kind of like a very quick, streamlined review of that chapter, of the capacitance chapter, which is kind of good to do, of course, as you're getting ready for the final. You're doing an overview of what you learned in each chapter. So the definition, the three main capacitors, what do dielectrics do, how do the capacitors add up in series, and variety of different capacitor circuits. Then you have a similar kind of routine with resistors. You have the definition of resistance, delta V over I. So notice that for resistance, the voltage is on the top, whereas capacitance, the voltage is on the bottom. And then the resistance depends on the current, whereas the capacitance depends on the charge. So then you do the resistance of a resistor, the current flowing this way. So you derive the resistance of a resistor. I don't think we did a cylindrical resistor or a spherical, but we could have derived an equation for those two, but we didn't do that. You could have a cylindrical resistor where the current is flowing cylindrically outward, and then a spherical resistor where it's flowing outward. But we just did mainly a straight line wire resistor. So that would be the main one. So that would be kind of like you're similar to the parallel plate. Okay, then what did we do? Then we talked about how does the resistance vary as a function of temperature, right? Then we talked about the series resistors. Series R total is R1 plus R2, and then parallel is opposite of the resistors. Now notice the way that it sort of works is that when the voltage is on the bottom in your definition, then it's usually going to work this way. They're going to add up like that. And then when the voltage is on the top, then they're going to add up like this. So that's kind of going to be the general pattern. And then we can have variety of resistor circuits, of course. R1, R2, R3. With resistor circuits, you don't really have a question like you have a charged resistor that's connected to an uncharged resistor, because resistors don't store charge. So you can't have problems like that, but you have more like resistors, or you can have light bulb problems. You can say, okay, you have a certain light bulb and you can say, okay, they have a certain rating. So which light bulb is the brightest? Which light bulb is the second brightest and third brightest? Those kind of problems. Then, of course, you can go to Kirchhoff's loops and say, well, what if we have two batteries, 2 or 3 resistors? Then that's just a more complicated version of this. But it's kind of a continuation with more batteries in the circuit. Then the next thing is the chapter 26 RC circuits, where you bring both of these in together and you say, okay, what if you have a battery, a resistor, and a capacitor, and then you're charging them, right? What kind of behavior does the voltage of the capacitor behave? We saw that the voltage of the capacitor charges asymptotically, voltage of the capacitor, until it reaches its final charging state, right? It reaches the voltage of the battery. And then the voltage of the resistor goes down all the way to 0. This is if it's a charging RC circuit. All right, so voltage of resistor. But then you can have variety of those kind of problems too. You can say you have a resistor, then you have a capacitor, another resistor, then you have another capacitor. You know, so we saw that you could have variety of problems, and I showed you how to solve problems like that. Sometimes you can even have one of the capacitors originally charged. The ones that I usually showed you were if there's multiple resistors but only one capacitor. When there's two capacitors, it makes it even harder. So let's say resistor R1, R2. These are more doable when there's only one capacitor. And then, so this capacitor can either be initially uncharged or initially charged. So then you analyze that circuit. So I showed you how to do that. So that's kind of been the routine for these, is define the concept, say what the resistance or the capacitance of your basic resistor and capacitor are, determine what the dielectric put in there will do, or in this case, how does the resistivity depend on the temperature, then determine how do they add up, then do circuits with them, and then combine resistance with the capacitor. So now it's going to be similar order of stuff. We're going to define what inductance is. Inductance, and the symbol for it is L. And the inductance is going to be negative EMF over di dt. So that's going to be your basic. It's going to take the role of this. And then EMF, by EMF, we just mean delta V also. Same thing. Delta V over di dt. Okay. So notice that if the delta V is on top, it's going to behave more like resistance. So when we add them in series, two inductors, they should add up like resistors. And when we add them in parallel, they should add up like resistors, because the delta V is on the top. The only difference is now that inductance relies on the rate of change of the current, whereas resistance is the current, but then the current is the rate of change of the charge, you see? So you could almost write this as delta V over dq dt, right? And then C is Q over delta V. So you have this is the certain variable, this is the derivative of that variable, and resistance depends on the derivative, and this is the second derivative of this variable, right? So it's negative delta V over d squared Q dt squared. Okay, so let's talk about the units of the inductance, and then let's talk about what are your basic inductors, and then let's talk about why there is a minus in the definition. So in terms of units, it would be what? Volts per amp per second, right? And then volts per amp is an ohm, right? So I guess you could say it's a ohm, volts per amp, and then the second goes to the top. So it's an ohm second, and then it gets a certain name called Henry. And so, well, Ohm gets a certain name because of the scientist Ohm. I believe his name was George Ohm. And then this is something Henry. So it gets its name based on that scientist's name. So that's in terms of the units. So now, why is there a negative? Well, what happens is that when, let's say, you have the typical inductor is going to look something like this. It's going to be like a solenoid, That's the typical way to draw an inductor in a circuit. So then what's going to happen is that when you connect this circuit, right, current is going to start going through this wire. And when the current starts going through the wire, you're all of a sudden going to introduce a B field this way. Right? Solenoid. So the current in the wire will create a B field. So now if I look at it from the eye this way, right, it looks like this. The solenoid will look like that. And then it's all of a sudden like a B field will be introduced out of the page, out of the board, right? Dot, dot, coming out of the board. So then what's going to happen in the solenoid? You should induce a back EMF, right? You should induce an EMF that will drive a current here. So which direction should that be? If all of a sudden I introduce a B field out of the board, the current induced in here should produce a B field to fight against that. So it should be like this, right? Clockwise as seen from this side. So if I draw like this, if the B field introduced is out of the board, then the induced current, I induced, should be what? Clockwise, CW, so that it will create a field into the board, right? The field created by that current. So this is kind of what we've been talking about the last chapter, all about Faraday's law, right? So therefore, the EMF induced in that coil, in this coil, is opposite to the direction of the external voltage, right? The voltage of the battery. The EMF induced is in the opposite direction, trying to fight against that, you see? So therefore, the EMF, this is the EMF induced. So this is delta V induced. So the idea behind this is that the inductance of an inductor is a measure of whatever rate of change of current that occurred, in the inductor to induce a certain EMF to fight against the external magnetic field and the external battery. So in other words, the thought process is that a certain di dt is occurring in the coil. That di dt is inducing a certain EMF. The bigger the EMF that it is inducing, the bigger the inductance of that inductor. So for a given rate of change of current, the bigger the induced EMF, the bigger the inductance. And the reason why it's negative is because the EMF induced here is acting opposite direction. It's acting as if it's a battery opposing the original battery, you see? So this EMF induced is technically negative, you see? So it's negative. So to make inductance positive, we say negative of negative, and that makes inductance positive. So that's why there is a negative there. Okay. Interesting concept, right? I think most people know more about resistance and maybe capacitance, but less people have heard of inductance. It's more of an advanced topic. Definition of inductance. Let's see here. Every day, the property of an electric conductor or circuit that causes an electromotive force to be generated by a change in the current flowing. Does that make sense? That's a more everyday type of definition. The property of an electric conductor or circuit that causes an electromotive force to be generated by the change in the current. You see? What is the inductance and its unit? Inductance. A current generated in a conductor by a changing magnetic field is proportional to the rate of change of the magnetic field. You see? This effect is called inductance and is given the symbol L. It is measured in units called henries, named after American physicist Joseph Henry, 1797 to 1878. And they talk about the units, L, Henry, and then they give you the breakdown of the dimensions, course, right? But it's actually the most applied. Okay, then they talk about transformers. What happened? Oh. Oh, okay, this is nice. This is on a certain table, they give you the main inductance of the main type of inductors. Single layer solenoid, coaxial cable, rectangular made of round wire, parallel wires, parallel wires. So those are the inductors of the variety of inductors that you can have. But maybe we could say, okay, what's a practical use? So if you were to say, what's the practical use of a capacitor? It is to store charge, right? So why even have inductors? So what's a practical, what's a practical use of inductors? So inductors are used as the energy storage device in many switched mode power supplies to produce DC current. The inductor supplies energy to the circuit to keep current flowing during the off switching periods and enables topographies where the output voltage is higher than the input voltage. Did you get that? It's kind of not that easy to get, but it's also, it seems like it's a energy storing device, right, to the circuit to keep current flowing during the off switching periods. So in other words, in an AC circuit, the source voltage is going to go up and down, and once in a while the voltage of the source is going to be zero, right, during the off switching periods. So during the off times, when the voltage of the source is zero, you already have energy stored in the inductor. So now the inductor is giving that energy back to the circuit. You see? Was that a good statement? Did that give you an idea? What is a practical inductor? What are inductors used for? List 5 applications. Inductors in tuned circuits, inductor sensors, energy storage devices, induction motors, transformers, inductive filters, chokes, ferrite beds, relays. So this is kind of getting a little bit more in depth into electronics, right, guys? Induction motors, transformers, inductive relays, and then you could kind of read up on the more specifics. All right, see, this is the symbol for inductance, L. Inductive sensors, induction coil, you see here. This is kind of nice. induction motors, transformers. Of course, transformer is very important. Inductive filters, chokes, relay. A relay is like an electrical switch. It uses inductor coil to control the current flow in it. When the AC current flows through the inductor of the relay, it produces a magnetic field which affects the switch contact. This one was, the first one was pretty easy to understand, I think. The very first one, the sensor, inductive sensors. Inductors are used in proximity sensors which work on the principle of inductance. We know that inductance is the phenomenon in which the magnetic field produced in the coil will oppose the flow of current in it. So thus the inductance will restrict the current flow and reduces the circuit performance. For better performances, we need to amplify the current in the circuit. We use proximity sensors to find the level of amplification factor at which we need to amplify the current. The manufacturers designed the sensors by twisting the wire into a tight coil like this one here. There are 4 components in the inductive proximity sensor. They are an inductor or coil, an oscillator, which is this guy, a detection circuit, and an output circuit. So you have the DC supply, oscillator generates AC current here, then it goes, and then this guy generates a magnetic field, and then it comes back to the current sensor, right? And then it comes back DC output. So you see what's happening is that when this guy produces AC current, that comes in here, creates a changing magnetic field here, right? And then this guy continues to produce back EMF. And then so the current red over here is due to the current produced by the oscillator plus the current produced by the back EMF of this guy. You see? So you see how it's producing a magnetic field here, the solenoid? But what's going to happen now, in the inductive proximity sensor, a fluctuating magnetic field is generated by the oscillator around the winding of the coil, which locates in the sensing face of the device. When an object moves in the field of inductive proximity area of detection, so imagine something blocks this, right? Let's say there's an object that blocks this area. So then it says when you're blocking that magnetic field, eddy currents start building up in the metal object, which will reduce the inductive sensor's magnetic field. You see, so when you're blocking this magnetic field somehow, that gets read by the current sensor, you see? So eddy currents start building up in the metal object. The strength of the oscillator is monitored by the detection circuit, and an output is triggered from the output circuitry when the oscillations are below the sufficient level. The inductive proximity sensor is a contactless sensor and is very reliable in operation. The inductive sensors are used at traffic lights to detect the traffic density. Ooh, I see. You see that? The inductive sensors are used at traffic lights to detect the traffic density. So where are they placed? Oh, they're probably placed on the road, right? When the car comes, let's say the car comes and blocks this, then it says, oh, okay, there's a car there, change it to green again, you see? So these are probably placed underneath the road, right by where the cars are supposed to stop. Oh, that was cool. I like that. That's why. Have you ever wondered why when you stop, then that turns the red to green quicker? And like if you kind of move up a little bit, and it turns it to green quicker than if you were not there, or if you had stopped a little bit farther away.